with the functional groups of just hydrocarbon only. And again, hydrocarbon is exactly that, hydrogens and carbons. And what we'll see now is going from alkanes to alkenes to alkynes. We introduce this concept of a degree of unsaturation. And so what that necessitates is that carbon can form more than one bond to another carbon, so double and triple bonds. And ultimately, where this will lead us to Monday is how can carbon do that? So on Monday, we'll talk about atomic orbitals, the limitation of atomic orbitals, and how they have to be changed into hybrid orbitals to account for the different bond lengths and bond angles we see in alkenes and alkynes. So today we'll just briefly review the alkene stuff, then we'll get into alkynes, then we'll talk about degrees of unsaturation and why that matters, and the logic of putting structures together from a molecular format. So I have some handwritten stuff up there first, but any questions we need to address?
How would you describe it?
So the degree of unsaturation, visually it's a double bond. Keep in mind that double bonds can be from carbon to carbon, carbon to oxygen, or carbon to nitrogen. The other form of a degree of unsaturation is a ring. So we'll see those examples today. So we had left off introducing alkenes. So again, pay attention to the subtlety of the names. Alkanes, we say, are fully saturated. An alkene has a carbon-carbon double bond. And so a double bond is a sigma bond. And then the second line is the pi bond. On Monday, we'll talk about what orbitals are involved in that. But that's defined as a degree of unsaturation. And so when we learn about the hybrid orbitals of carbon, we'll talk about saturation, how many sigma bonds, how many pi bonds are involved in each type of hybrid orbital. So we saw the carbon count here. So for two carbons, again, the first part of the name tells you the number of carbons involved. The second part of the name, the suffix, let me erase that. So the first part, number of carbons, the parent. So remember, we need to know C1 to C10 names. The last part is telling you the major functional group. Since this ends in ENE, that functional group is an alkene. So 2 carbons, that's ethene. 3 carbons is propene. 4 carbons is where we get to now. We can have more than one compound for the molecular formula. So I drew the first one out. This is 1-butene. This number here, in the nomenclature rules, it's called a locant. And so you have the number, a hyphen, and what it's doing is specifying the first carbon of the double bond. So the double bond is starting at carbon 1. So that's what this 1 means. Nomenclature is interesting because there's the formal rules, but common uses still, are used. This might also be written as BUT-1-ene, and that just moves the number closer to the functional group. But what if the alkene started at carbon 2? Now there's two situations in which, two isomers in which you can draw. The relationship between these is called geometrical. And that's the geometry about the double bond. So how do we differentiate them if they're both 2-butene? So let me highlight these carbons, 2 and 3. Those carbons are sp2 hybridized. Visually, they have 3 sigma bonds and 1 pi bond. So once you highlight those, then you're looking for any non-hydrogen substituent bonded to those and seeing if they're on the same or opposite faces. So the first one, the methyl groups at 1 and 4 are on opposite faces, so that's trans. So this is trans 2-butene. The second one, 1 and 4 are on the same face, so that's cis. Yep. The question was, what do I mean by face? So imagine like an axis drawn through there. You have sort of this like right face and then this left face. Or side, however, whatever word you want to use for that. So these 3 would all be called linear. All the carbons, if you start from carbon 1, go to 2 to 3 to 4, that's a linear chain you're walking on. So there's another 4th isomer of that molecular formula, which would be branched. And so if it's branched, it has to be less than 4 carbons, so 3. So there's 3 carbons. We'll plunk in a double bond because it needs it. And then we need to add the 4th carbon. So when we do this, it can only go on carbon 2. If we put it on the ends, 1 or 3, we're just making something we already made. So one thing I want to point out in the prior case, see this trans compound? The substituents on carbon 2 are different. You have a methyl group at carbon 1, and then you have a hydrogen. Now in this case, since both hydrogen, hydrogen, methyl, methyl, they're the same, there's no cis or trans here. Meaning this methyl group sees a hydrogen, this methyl group sees a hydrogen, so you don't need to specify any geometrical cis or trans. This would be called 2-methyl 1-propene. Yeah.
Is the 1 necessary?
So the question is the 1 necessary? In theory, not, because there's nowhere else you can put it. I'm just showing it as, since we're learning this stuff, just to include it. But ultimately, you can't draw any other compound with the double bond, so that number would be different. So those are C2 to C4, and I definitely encourage you to go back to the prior slide from Wednesday. Draw out the C5s, the C6, so that you practice doing this. Question?
Yeah, what does laser FG mean?
So that's the FG is functional group.
So the end or the suffix of the name is telling you what functional group takes priority. So now going up to the next hydrocarbon functional group, alkynes and YNE. So that means they have a triple bond. So carbon-carbon triple bond. Those carbons are sp hybridized. So they have 2 sigma bonds plus 2 pi bonds. And I'll use these models in a slide coming up on the doc cam to show you those bonds. The molecular formula for an alkyne is CnH2n minus 2. Question up in the middle there?
Yes, I was kind of confused on how to determine like the cis versus trans thing. Like, I don't understand how that works.
So let me go through this, and then when I get back to this, we'll answer that. So here's the carbon counts. There's no C1 alkyne. You need 2 carbons for an alkyne. And then the lines I've just drawn, notice that once you get past 3 into 4, 5, and 6 and beyond, that's when you can start having more than 1 compound per that molecular formula. So again, those are constitutional isomers. So C2 is ethyne. Again, the eth tells you it's 2 carbons. The YNE tells you there's a triple bond. There's the molecular formula, the weight. I've neglected to put in the physical states for this for some reason. But it's a gas. It's also called acetylene. Any metal fabricators in the crowd? No one's worked in a garage. So if you've heard of oxyacetylene, so an oxyacetylene torch is what is used to cut metal. Obviously, you need oxygen for fire. The acetylene is the fuel source. We'll talk about why hydrocarbons make good fuel sources, like for your automobile. When they combust, they put out energy. That's what sort of turns the piston in an engine. It drives the drive shaft, turning your wheels so you can show up to class. The uniquenesses are shown here, unique ni. I don't know if it's proper plural term, but you can go through those as you draw them out and determine the unique carbons and hydrogens as practice. So carbon 3 is propyne. Again, notice the molecular formula C3H4. So again, CnH2n minus 2 is that molecular formula for alkynes. Now when we get up to 4, we have this locant number which specifies the start of the triple bond. So 1 butyne, 2 butyne. And really, terms we would want to use for alkynes are internal versus external, or terminal. So let me write that down. So this would be terminal. This would be internal. And on the next slide, we'll go through C2 to C4 structures so you can see what they are. Again, we haven't formally gone through the nomenclature rules, but hopefully you start seeing the basic trends of how things are named, organic compounds are named. So again, the but tells you the carbon count. We have that line, YNE, that's telling us that the major functional group is a triple bond. So alkynes will have a carbon-carbon triple bond, and now each pi bond is a degree of unsaturation. So that's 2 degrees of unsaturation. To achieve that, the carbon has to be sp hybridized, which is 2 sigma bonds, 2 pi bonds. So visually, you're just counting now. Does the carbon have those 2 double bonds, which means it also has 2 sigma bonds, so it's sp hybridized. sp3, sp2, sp we'll talk about on Monday. Basically how they arise from atomic orbitals. So there is ethine or acetylene. There's propyne. I've explicitly shown those hydrogens, but I could also draw it like this. And students will often get confused about this representation here. Just remember that that's a carbon at the end bonded to another carbon. So that's a carbon right in the middle there. I'm showing this bond here. This whole thing is straight rather than bending it. Rather than that. The reason this is wrong is because, as we will see, there are certain bond lengths and angles for the different hybridization states of carbon. For an sp hybridized carbon, the geometry has to be linear. So that's why we draw this all in a straight line right there. So this, when you draw it bent, that's not the best representation. So for the 4 carbon count, we said there were 2 constitutional isomers. We start the triple bond on carbon 1. And you'll see once we have that substituent off carbon 3, we can get back to the normal sort of bent drawing. So this is 1 butene. And the other constitutional isomer will migrate the triple bond starting to carbon 2. So 1 butene is considered a terminal alkyne because you have, it's at the end of the chain and you have this CH group. The 2 butene is internal because carbons 2 and 3 are both bonded to carbon. So those are some nomenclature rules and descriptors of the class of alkynes. Any questions?
Could you draw
3-methyl 1-butene. So 3-methyl 1-butene, that's going to be a 5 carbon. alkyne. And as I said, in this class, we learn things sort of in the forward direction, we learn them in the back direction. So what we're doing is taking a name and we want to draw a structure. So the way that I think about this, you read 3-methyl-1-butene left to right, but you sort of draw it right to left. So we see that, okay, there's a triple bond. The longest chain is 4 carbons, and the triple bond has to start at carbon 1. So I've done the main parent part of the molecule. Then I look at what's left over, and this is called a substituent. We know meth is 1 carbon. When it's methyl, it's a substituent. It's bonded to the 3 position, so we would put it there. So that would be 3-methyl-1-butene. So this one has the angle here. I don't consider that branched. It's still linear. I'm just drawing, that sort of vertex this way because that carbon is sp3 hybridized. And those are both sp hybridized.
Okay, I understand what I was getting confused now.
Okay.
Thank you. I was mixing the SP and the SP. Yeah.
Okay.
Thank you.
So just as a quick review, what suffix should each hydrocarbon have if it has a single or sigma bond, sigma plus pi, or sigma plus pi plus pi? Any guesses? C. So alkanes, alkenes, alkynes. Yep.
On Monday, when we go over the hybridization and the orbitals a little more, will that specify why some alkenes can be linear and why some can't be branched and why others can't be?
Not really. The hybridization really, remember, carbon only forms 4 bonds, but what this is telling us is those type of bonds can be different. So in an alkane, there's 4 sigma bonds. The alkene, it's 3 sigma bonds plus 1 pi bond. And then the alkynes, it's 2 sigma bonds plus 2 pi bonds. To get to your answer of that question, if the molecular formula allows for it to be branched, it can be. Really, you just have to put pencil to paper and draw them out.
Okay. I guess I was just confused on why protein could not have like the angle, but then when we went to 4 to 5, they could have the angles on the previous slide.
So here is a summary of hydrocarbon functional groups. Alkanes, alkenes, alkynes from C2 to C4, what constitutional isomers you could have. So we have the carbon count here, then linear versus branched. So for alkanes, the C2 is ethane, C3 is propane, C4 is butane. Then you can get into these branched things down that column. So that would be 2-methylpropane. Cycloalkanes, the smallest ring size is 3, so that's why there's nothing here. So cyclopropane, cyclobutane. Then if you had a branched C4, that would be methyl cyclopropane. Alkenes, ethene, prop-1-ene. We saw the 3 constitutional isomers that are linear for C4. But-1-ene. Notice I've used something different here, E and Z. That is equivalent to trans and cis. So E is trans, Z is cis. They mean the same thing. We'll talk more about those during the nomenclature lecture. A branched C4 is the 2-methyl-prop-1-ene. So the E and Z, those are called geometrical isomers. Alkynes, we have ethyne, prop-1-ine, but-1-ine, but-2-ine. So terminal versus internal. So here's a question. If you had 7 carbons, how many total hydrogens should each functional group have? So this is CnH2n plus 2, CnH2n, 2n, and for alkyne, CnH2n minus 2. So if we have n equals 7, 2n plus 2 for alkane, so 2 times 7, 14 plus 2 is 16. And then you can see that we're just subtracting 2 off for each one. So that should be C. So alkanes, no degrees of unsaturation. Alkenes, 1. Alkynes, 2. So when you look at the progression of these molecular formulas, each molecular formula is losing H2. So 1 degree of unsaturation, really experimentally what it's equal to is 1 equivalent of H2. So this question asks, is C8H18 saturated? Saturated means there are 0 degrees of unsaturation. So when n equals 8, we plug that into 2n plus 2. We get 16 plus 2, that equals 18. Those numbers are the same. So is the molecular formula saturated? That's yes. If they were different, then there would be a degree or more of unsaturation. So for octane, 1 octene, 1 octyne, how many double bonds should each have? So the octane, ANE, is fully saturated, so that has 0. The alkene has a carbon-carbon double bond, so that's 1 degree of unsaturation. The octyne has a triple bond. So a triple bond is 2 pi bonds, so that's 2 degrees of unsaturation. So our answer here would be B, 0, 1, and 2. So I'm drinking from a Red Bull. Hopefully you're not drinking from the fire hose, as they say. Again, there's a lot of information in this class, and you have to digest it accordingly. And what that means is, outside of this 60 minutes, each day you should be putting some time towards the class, reviewing and doing problems. As we move along, we're getting farther and farther away from general chemistry. And so newer and newer things are showing up. And you want to make sure that, you're not drowning in it. Okay, so let me switch over to this real quick. So this is a model kit that's sort of like the ball and stick. The black atoms are carbon. The white atoms are hydrogen. And so this is ethane. So 2 carbons. Each carbon has 3 hydrogens, so 6. So that's fully saturated. And again, the meaning of that, can't look in 2 places at once. So I'm going to point here, and hopefully I'm on screen. So this carbon has 1, 2, 3, 4 sigma bonds. That's fully saturated. It has 2 types of bonds, a carbon-carbon sigma bond and then a carbon-hydrogen sigma bond. The other thing I want to point out, that central bond, the sigma bond, you can rotate. So there's free rotation. And that will become important when we move on into Module 3 and talk about conformers. The next one, there's, again, 2 carbons, but now there's 2 less hydrogens. So there's 4 total hydrogens. So notice there's still this central bond. That's a sigma bond. Then this other thing here, that's the double bond. The double bond is consisting of a p orbital on this carbon, a p orbital on that carbon, and then these things in here are the bond between them. So in a sigma bond, the pi bond actually resides above and below that. But we represent it as that second line when we're drawing it. So this is a pi orbital. Notice that see these different colors of that p orbital? That corresponds to a mathematical sign or a phase. And so the pinks line up, the purples line up, they're phased properly, so they form that bond. We're not going to talk about the math of these orbitals. It's more of a visual learning tool. So notice when I grab both of these carbons, I can twist it a little bit, but I can't fully rotate it like I can this. So that has free rotation. When you have the double bond, it rotates a little, but I can't fully rotate it 180 degrees. The reason being is that pi bond locks it in place. And so we said the triple bond has 2 pi bonds. So now it's C2H2, 2 less hydrogens than the alkene. So each carbon atom is now supplying 2 p orbitals And if you look, those orbitals are in different planes. So you have one this way, and then you have one 90 degrees to that. The second one, that's orthogonal. And these definitely will not rotate at all. The consequence of that is as you increase the number of bonds between both carbons, the bond energy gets stronger. So it's easier to break a single bond than it is a double bond, than it is a triple bond. Yep.
What's
Orthogonal means 90 degrees.
Oh.
So the other thing, I'll bring these back on Monday. We'll talk about HCC. You need 3 points to define an angle, right? So those 3 points, HCC, that defines an angle. Just looking at that, boom, 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 versus looking at it for the alkene, H carbon carbon, the bond angle is different. And then finally the alkyne, HCC, this is probably the most obvious one, that bond angle is 180 degrees. So visually when you're looking at counting sigma and pi bonds, that relates to hybridization. Hybridization changes the shape. You remember Vesper theory, the different shapes of molecules? And then ultimately that impacts the function of the molecule. So for the last 23 minutes of today's lecture, we're going to talk more about the degrees of unsaturation. And I really can't stress this enough. Being able to do this and figure that number out will allow you to take a molecular formula and figure out what functional groups you can have in it and what functional groups you cannot have in it. So again, it's important to not only define something by what's there, but by what is not there. So what do I mean by that? Hydrocarbons are C and H only. And remember in AZT there was an alcohol. So an alcohol has an OH group. So I can look at this molecular formula C4H6 and I can tell you with 100% confidence there is no alcohol in that molecular formula because there's no oxygen specified. So if you're drawing a structure and you put an alcohol in there, you're immediately wrong. And so that's the self-check. C4H6, notice I haven't given you a structure, right? So if there's no structure, how do you figure out the degrees of unsaturation? So for a fully saturated hydrocarbon, again, that's an alkane. So you have N carbons, there must be 2N plus 2 hydrogens. And the molecular formula of that is CnH2n plus 2. So we need to just commit that to memory. So that's the theoretical. Then we're given C4H6. And so for that carbon count 4, we need to determine what is the maximum number of hydrogens we can have. So we plug it in. 2 times 4 is 8, plus the 2, that gets us 10. 4 carbon atoms should have a maximum of 10 hydrogen atoms. So C4 H10. We're given C4H6. We do organic chemistry math. The C4s cancel. H10 minus H6 is H4. And I said in the prior slide that a degree of unsaturation is one equivalent of H2. So we then divide that by H2. So 4 divided by 2 is 2. So why is that? Again, H2 is, if you were to figure this out experimentally, you take hydrogen gas, react it with your unknown substrate. You use the ideal gas law, PV equals nRT. You solve for N, where N is the number of moles. You can figure out how many moles of hydrogen gas are taken up by that molecule. So we get 2 degrees of unsaturation. A degree of unsaturation can be a pi bond or a ring. So we'll do like 2 or 3 questions, and then we'll put this into practice where we take that C4H6 and we start proposing structures from it. What can we draw given that constraint? So first, question?
So let's say you have a larger hydrocarbon with multiple double bonds or triple bonds in different places. Will that still apply, or would you
So this is a good exercise to answer your question. So we want to calculate the degrees of unsaturation for C10H12. And then I'll get back to your question. So given N equals 10, so 10 carbon should have 22 hydrogens. So we take what it should be, subtract out what it is. That gets us H10. We then divide that by 2, so we get 5. So that molecular formula has 5 degrees of unsaturation. And so then the next exercise is, can you start drawing structures that have 5 degrees of unsaturation? So we'll ultimately provide more data for doing this through IR, NMR, and mass spec, where you're really, of all the possibilities it could be, given this data, what is it? So is C6H16 a reasonable molecular formula? I heard a no. Why not? So it should be C6H14. So again, for N equals 6, The maximum number of hydrogens is 14. So that's why you want to use that CnH2n plus 2. What's the maximum? So this is another self-check of saying, okay, that molecular formula cannot exist. So this is sort of the Willy Wonka slide here, using your imagination. You're given a molecular formula using, the Lewis dot rules as the constraint. You don't want to violate them. Of that molecular formula, how many structures can you propose? And then of those structures, how do you differentiate them with carbon and proton uniqueness? And this exercise is meant to help you start drawing things, learning the different functional groups. Notice, again, there's no heteroatoms in here. There's no O, N, or halogens. We'll cover that next week. There's subtle differences you have to account for. But you do this practice with the hydrocarbons, then when we start including the heteroatoms, that's when you learn those other functional groups. So how do we logically do this? There's a table on the next slide we'll use. What's the uniqueness? How do we differentiate them? And towards the end of this module, we'll talk more about physical properties. Again, those are just pieces of data you look up, you Google it, or if need be, I'll put it right on the test so you can do a comparison. There's no need to commit that sort of thing to memory. It's not important. You just look it up. And of that, so let me just write a quick note. So hybridization of the carbons gives it a shape. You have these overall shapes. Are things linear? Are they more sort of spherical? And those are the explanations to explain how melting and boiling points differ. So as you have longer and longer chains, they become more entangled like spaghetti. That means you have to put more heat to separate them. That would increase like a boiling point. If you just have things that look sort of spherical like M&Ms or like meatballs, they're not entangled with one another. So as you add heat, it's easier to boil them off. We'll talk about those things probably the end of next week. So what? Monday is no class, right? So don't show up because I won't be here. So what we're trying to do is take this molecular formula C4H6 and then draw structures in a logical way that accounts for the 2 degrees of unsaturation. So remember, if a degree of unsaturation is a pi bond or a ring, we have 2 of them. What are the combinations? In the second column, they can both be pi bonds, which would then mean you can have 2 alkenes or 1 alkyne. The third column, you can have a pi bond and a ring. The fourth column, they can both be rings. So in a linear sense, if we have 4 carbon atoms and we need to stick 2 pi bonds in there, so there's 4 carbon atoms. We could put one at position 1 and the second one at position 3. So since that has 2 double bonds, it's called a diene. What if it was a triple bond? That would be a terminal alkyne. We could have it internal, so CH3, triple bond. CH3. So you would use the uniqueness to differentiate them. And then when we actually start seeing IR and NMR data, you know, if you are given a carbon NMR or a proton NMR and the choices for the question were, is it A, this structure, B, this structure, etc., you would use the data, then match it up with the uniqueness. So what about, when I say linear for a ring, I'm taking 4 carbons and making that size ring. So that's a degree of unsaturation. Now, if I have to add a second one, I would just put a pi bond in there. So this would be called a cyclobutene. What about 2 rings? Could we draw 2 rings with 4 carbons? Not necessarily in this row. If we were to draw a 4-membered ring, that takes up all the carbons. But we can, and I'll draw it in the bottom row. If we wanted to do branched, is there a branched for 4? Can't think of one off the top of my head. We'll circle back if we do. So 3-membered ring. So we're down to 3 now. Let's draw a 3-membered ring. So a cyclopropane, that's a degree of unsaturation. We need another carbon and then a pi bond. So we could put a carbon here. Oop. We could then add the pi bond there. Or say we could do that, but then we put the pi bond in the ring. So that's perfectly valid. And then what about 2 rings? So I said we couldn't do that, but if we make a bond between carbons 2 and 4, now we have 2 rings. So that's 2 degrees of unsaturation. Each is a ring. So to recap, the point of doing this exercise is to get you used to drawing structures and figuring out, okay, does it obey the degrees of unsaturation? Does it obey Lewis dot? How do I do the uniqueness? Because that will differentiate them. Is a question?
For the high ring free branch, would it be a different molecule if the double bond is like across the metal?
So that'd be another one. What you'll find with this type of problem, especially when we start adding heteroatoms in, like these are not small sets of compounds you can draw. I mean, you can get past 20, 30 different constitutional isomers. And the point again of it is, okay, I know since I have an oxygen now, I can draw an alcohol, or I can draw a ketone or an aldehyde, these different things, and that gets you used to identifying the name associated with that functional group. So just the last couple questions here based on those structures as a review. Which of the following is not a viable constitutional isomer of C4H6? Huh? It's like Mr. Tiber, my high school algebra teacher, huh? So B, why is B not? So it has 5 carbons. So that's a cheap trick for exams. Count your carbons, make sure that you're not sort of misreading things. Which of the following is an alkyne? So that's C, there's our triple bond. So alkyne is the triple bond. Which of the following has a uniqueness set of 2 unique carbons, 2 unique sets of hydrogen with the ratio of 4:2? So we already eliminated B as, it can't be C because there's only one unique set of H, and that's 6. Trying to see if this is ambiguous or not, if I sort of screwed myself on the hydrogen uniqueness. I have the answer written as A, but in a sense, D could be that as well. So for A, you have 2 plus 2, that's your 4, and then you have this H, that's that 2. But D has symmetry, right? So this could be H, 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 H. That would be 4. These H's would be 2. So that's not a very good question in a sense. There's something about D that makes it a little different. I don't want to explain it now, but I won't dig the hole any deeper than I'm in right now. So basically, the last slide was just any questions before we wrap up. Your quiz is posted in ZipGrade. Make sure you do that. And then next Wednesday, I think I said Monday before, next Wednesday we will start with the atomic orbitals and hybridization.